the materials lab.
So we saw this last time, and we integrated. Now we're going to do it, solve for the reactions without integration. As far as the longitudinal direction, it's the same as before. We have the summation of forces, so the x is 0, this being x, the horizontal direction. So we have r sub ax must be 0 because there are no other loads and no other reactions either in that longitudinal direction. So this is 0, that's what we found before. And then let's solve, we'll sum moments about B, so this is A and B. And the applied loading on this structure is a distributed load that's varying. And so you have to sort of come to terms with that in your head, what that is. So this is, at each point is kips per foot and is increasing, right? So the end is, the intensity is 20 kips per foot. So if it were constant over the whole thing, it'd be 20 kips per foot along each foot over the whole length. But it's varying. So it's 0 here, no distributed load. At this point, the intensity of the distributed load is 10 kips per foot, and at the right is 20 kips per foot, and it's increasing as we go. And that's why we have to do something to recognize that distribution. In this case, it's a triangular distribution, and so we can say, okay, well, we can solve for r sub a y by saying summation of moments about B is 0. And that gives me r sub a y multiplied by 30. So the applied loading doesn't have anything to do with the moment associated with this, right? This is reaction AY times length in terms of the equation at least. It has the actual final value of r sub AY, it has a lot to do. So that's the clockwise moment about an axis coming out of B from this reaction, right? This horizontal reaction, even if we had a value, it's going right through B. And so the contribution to the moment equation about B is 0, even if this had a value, right? Because it's that force times 0 to normal distance. And then that equals, and so again, instead of last time we integrated using calculus, the last time we had each one of these little guys, we represented as dp, right? When we did calculus. And this was dx. And the intensity at any given point is W, given us an equation. And so we had, and then the distance there, we could say was the moment arm here. Let's say little m. So we had the differential m was equal to m, let's call that A, was equal to dp times A. And then we used, and then dp was equal to W times dx. And so then we just summed all of those. We ended up with an integral, a basic integral that we can integrate. We did that last time. So this time, instead of doing that, we're just taking the total area of the distributed load. So imagine it's an area of a triangle. So it's 20 kips per foot multiplied by the length of 30 divided by 2. So that's the total force. And then what we want to do, that's the total force applied. This would be in kips, right? This is kips per foot multiplied by a distance divided by 2. A distance is in feet, so this is a force, and then we need to multiply, that's the total force down. It's the same as if we integrated this part of it. And then we need to multiply that by a moment arm, and the moment arm for a triangular area is to the centroid. So it's 1/3 the distance. Here's our centroid location of the triangle. And we're just interested in the horizontal position of the centroid. The centroid is if you have, we're going to be talking about that in this class, and deriving centroid equations for different shapes, complicated shapes too, using calculus in that case. But, and you can use calculus and derive this, but this is, if this is 30, let's call this L. This is L over 3. This exact. That's the same. So if you cut this out of cardboard, let's say it turned it flat, that would be the point you would put your finger to balance it, so it's balanced. That's the balancing point. And so what we do is take the total load, that's the total applied load down, and then we multiply it by the moment arm, L over 3. This is equal to 10 feet, right? So multiplied by 10. This is the moment arm about B. And this 10 is 30 over. So that 30 cancels, and we get R sub A y is 100. Yeah. So yeah, 30 divided by 30, you have 20 over 2, which is 10 times 10, you have 100 kilos. Okay, so, and then reaction B, we just use again summation of forces vertically, right? Summation of forces in the y is 0. This is all based on physics, you know, Newton's equations, not just equations of motion, mass times acceleration is force, but the equations of statics. And so summation of forces in y, for this to not be dynamic, to not have, if you apply a force that isn't balanced, then that has to be balanced by mass times acceleration. Mass times acceleration means it's accelerating, and this is a statics problem, right? The structure's just, yeah.
Basically, like the summation of forces of x or y, if they equal the actual positive number, that means it would be fluid.
Yeah, that would be equal to the mass times acceleration. If you had it, if it didn't equal 0, if forces in the x is 0, forces in the y is not equal to 0, it would be accelerating. And accelerating equal to the mass of the structure. The mass is just the weight divided by g, gravity, which would be 32.2 feet per second squared in English units. And so that would mean it's accelerating. That's the second part of this course. That's dynamics. But right now we're talking about statics, and so that's why they have to set it to 0. So we have reaction B plus 100, which is reaction A. Just realized the cleaning staffers are leaving the office. I hope they're not surprised. Go in my office and there's this wild dog. Okay, so R sub B times plus 100 equals the weight down. Now again, we'll just use the total area to get the total weight, just like we did here. So that's 20. So it's just the area of a triangle, right? Area of a rectangle would be the height times the width, and that would be doubled, and we want 1/2 of that. So that's why it's just 20 multiplied by 30 over 2. Then we can solve for reaction. Gives. And its total force down is 300, right? It's 20 times 30 over 2. So it's 300 kips, and you can see so the reactions 100 here and 200 balance the total load down. Yeah.
For the triangle, like for the centroid, we can always use like 1/3 of the total distance to find the centroid distance.
for a triangular shape, it's always at 1/3 if you're going from this side, and 2/3 if you're going from this side. So if the triangle's turned around, it's 2/3.
Gotcha.
So as you can see, for this type of a case, for a simple shape of distributed load, it's much easier than using calculus to solve this problem, much faster. Same results. This is another truss structure. Height of 50 feet, same spacing. Width of 40 feet. Vertical load, evenly distributed. So this is 5 kips per foot across the whole thing. It's not bearing. And then we also have a lateral load of 10 kips per foot, triangular like this. And this is consistent with, it could be wind loading, lateral loading, or earthquake loading. Earthquake loading is inverse triangular like this typically, or at least approximately. It has to do with the reason it would be inverse triangular in earthquake loading is the force that any part feels is the mass times acceleration. Let's say each floor, as you go down, it has a, let's say, constant mass distribution, a weight distribution, and the structure as it's under earthquake loading, it displaces approximately like this linear increase. So your accelerations would be larger at the higher part of the structure than the lower. So you end up seeing a distributed load from earthquake loading that looks something like this, inverse triangle. We have, this is the maximum, 10 kips per foot, and at the bottom it's 0. This is reaction AX. Reaction AY, and reaction B. So first, let's do a summation of forces in the X is 0. And in this case, it's not going to be trivial. We actually have a value because you have this large lateral force that wants to push the building and roll it to the right, and it's being prevented by this reaction, not by the roller B. It's not taking anything, right? So we get reaction AX is, and now we just need to find, we're summing forces, so this is a force to the left, the reaction, with no movement, and then the force to the right is this whole area, right? So it's just 10 kips per foot, so it's 10. It's a triangular area, so it's 10 times the height of 50 divided by 2. So we get 250 kips. And again, a kip is 1,000 pounds, so that's 250,000 pounds. That's the same, the big machine that we tested the log on yesterday, that's the same capacity as the machine. We can apply 250,000 pounds. The logs didn't take that much, but there are other things we tested that can. So 250 kips. And then let's solve for the reaction of B. If we're going to be, if the next step is solve for the reaction of B, we need to take moments about A. And then there's another thing. You can't use the same equations multiple times. For example, summing moments, you can't say, okay, I'm going to sum the moments at A, I'm going to sum the moments at B, and I'm going to sum the moments somewhere else. You you have three independent equations that you need to use to solve for three unknowns, right? And that's the way equations work. If you have three unknowns, you need three independent equations, not three the same equations. And so that's why we're using this. And then we use summation of moments about a point, and then we use summation of forces in the y. Those are the three equations available to us from science. Now we have summation of moments about A is 0, and I could have done about B either way, but so once I solve for summation of moments about A, it's because I'm solving for the reaction. Okay. And I'm doing that, I'm intentionally choosing this location so that the other unknown, r sub A y, isn't included in this equation. I'm eliminating that so I can solve for r sub B. If I sum moments, let's say somewhere else in the middle of the structure, I would have an unknown, two unknowns, right? Okay, and or I could solve some moments about B, and then the only unknown in that equation would be r sub A y. And I could solve that. And then the third one would be solved for by summing forces. So summing moments about A is 0. We have three different moment contributions from three different, there's the reaction of B, of course. So counterclockwise, I have r sub B, which is what I'm looking for, multiplied by 40. That's counterclockwise about an axis coming out of the page here, right? Counterclockwise equals, the other two are providing clockwise moments. Let's start with the distributed load, evenly distributed load at the top. That equals, so is 5 multiplied by 40. That's the total load down, right? And I put square brackets around that so you know that's different than the moment arm. And then if I take a line here, this distance is 20. So I multiply, that's to the centroid of the applied loading, right? That's my moment arm, so that's 20. And you can see that that's producing a clockwise moment about A. So you always have to say with respect to y. You know, it's not a clockwise moment. If I was summing moments about B, it would be a counterclockwise moment from that same distributed load, okay? But in this case, I said ahead of time, I'm summing moments about A. The centroid of this force is acting here times this distance that's clearly producing a clockwise moment. And then I have this distributed load. I say plus 10 kips per foot to the total load now to the right. Applied load 10 times 50 over 2. Right? And then multiplied by the distance to the centroid, this distance, which is 2/3 of the height, which is 50, right? That's my moment arm for that load. So times 2/3. And then the only unknown then is r sub B. These twos cancel, simplifies a little, and then you solve for this 308 kips. And then after that, so the only unknown now is reaction AY, and we have the third equation, which is for summing the forces vertically. So we have summation of forces and the y is 0. And now be very careful, because notice the way I drew this arrow. I'm drawing it down, that's my positive definition. So that's in the same, so this lateral load that varies over the height, that doesn't contribute to the vertical, right? All I have is r sub AY, r sub B, and the 5 kips per foot. But the way I drew this down, this is in the same direction as that. So I have to recognize that when I write the equation, as opposed to what's positive, what's negative. I have 308, well, R sub A y, which is my unknown, plus 5 times 40 equals 308. So this is 108 kips, and it's in the downward direction. So because of this large lateral load, if we didn't have a lateral load, both reactions would be up, and in this case, because the vertical load is distributed evenly, they would be equal to 2 vertical reactions. What happens is the lateral load increases this reaction, right, and decreases this to the point that it's actually tension is pulling down on the structure. So it's preventing the structure from overturning. If we allow this to lift off, it would want to rotate about this point, even if we prevented it from sliding, let's say, but didn't give a pin vertically, it would rotate about B and lift up into the air. So this is holding it down, okay? And then this force is large pushing at all the static strings. Is that clear? So if you get the statics wrong when you're doing, I mean, right now we're just looking at applied loads and reactions, but in structural engineering we go further. We're determining the actual deformations, displacements of all the different points in the structure, the stresses and the strains and the forces, the moments, shears, axial forces throughout. And then you're designing the structure so that it doesn't collapse under all the different load cases you're considering. So with that in mind, let's now look at shear and moment diagrams for beams. This is important. So what I'm going to say here was that we're applying loads, and right now we're just solving for the reactions. If you get your reactions wrong, then the rest of your structural analysis will all be wrong. And there's a long history of doing hand calculations, being able to solve things like what we're doing here. These are called hand calculations, as opposed to just blindly putting something in a computer program and having it spit out all the results. And even to this day, designers, when I design a structure or do analysis of a structure, I always, 100% of the time, I independently check by hand calculations and verify results by computer. Otherwise, there are all kinds of possible errors from computer. It's not necessarily the computer program is wrong, although that's also a possibility. There are errors in computer programs. But if the user is not that familiar with the program, either input or output, there are always possibilities of errors. So hand calculations in the old days, of course, before computers, and then even when computers first came online, also, I mean, structures have been designed for for hundreds and hundreds of years, and they were done by hand calculations. And still, there are methods as you go through more advanced structural analysis classes, including Civil Engineering 321. I teach you methods for solving problems by hand, not just jumping on the computer. And you get the same results as the computer, so it's important to understand that. So whenever I've designed structures or done analysis or decided retrofitted structures, I always verify. And sometimes I've designed structures, complete bridge structures, even large structures, by hand calculation, and then I checked it by computer. So sometimes, typically, you design it by computer and you check. I check the results by hand calculations, and then in that case, I'm just spot checking results for the longer span, the maximum, minimum in the span, maximum axial force in the column under different loading cases, things like that. Spot check results, 10 or 20 results, and you're getting 99% the same result as the computer program. You can get closer if you want, but that's good enough. That gives you a sense of security, that your results are, the computer program results are reasonable. But either way, either you're designing and doing analysis by computer or by hand, and then you're checking independently with the other method. You don't typically do an analysis and then do an independent check on a computer program, especially if the program at the base is the same source code, because it's just, if there's an error in one, it's going to be the same exact error as the other. So hand calculations are very important. Okay, so with that in mind, let's talk about this. So we're going to start simply and then get more advanced. Here's a beam. Again, one side is pinned, the other side's a roller for the same reasons we talked about before. I'm going to apply a load in the middle, a vertical load, force, 10 kibs, so it's 10,000 pounds being applied down. The structure, the total length is 20 feet. This is applied in the middle, so it's 10 feet on each side. We'll label the locations A, B, C. Not happy with that, let's reschedule. This is greatly exaggerated, but that's the display shape. There's zero vertical displacement at the end supports. There's rotation here because the two ends cannot hold a moment. So we know ahead of time that the moments, the bending moments, are going to be zero. The shears, we can solve for the reactions as we've been doing. This is zero in this case. You can see this is by statics and symmetry together. This is 5 and this is 5, right? The two reactions, because the load's in the middle, the two reactions are going to be the same, and they sum up to the applied load. And then this is the deformed shape. Let's look at the shear diagram. So the shear moment diagram, let's talk about that. This is in kips. Every cross section of this beam, as we go across, as you enter into the structure with this load applied, every cross section. So this beam, this is a single line just drawn along the centroid of whatever the cross section looks like. And this deflecting. But it feels the whole cross section of that beam, if it's an I section, it's a rectangular section, whatever it is, it has to resist 5 kips, right? If I take a cut right there, there's a force up of 5 kips. And if I take a cut here, that's still 5 kips, right? There's a force up. That the whole cross section is resisting it through shear stresses. Shear stresses of V2 over IV. There's also a bending moment, but let's talk about that in a minute. So, and until we get to this point, you can see if there are no loads applied down or up along that length, up until we get to some load, like 10 kips, every section is resisting, feeling at 5 kips. And if it overloads the structure, then it won't be resisting it and it will fail, right? You'll yield damage and fail the structure. So we come to this point, it's constant, so you stay fine like that. And then now imagine, and it's still true, you're pushing up on every cross section as you go along, 5 kips. You cross C and it's 5 minus 10, so it's minus 5 kips. It still feels, in this case, 5, but it's pushing down now. Like if this 5 wasn't here, it would just be a 10 kips down at each cross section. But you have to sum everything as you go across. Right? So here it drops to minus 5. And this is the shear diagram. That's A, C, and B. And then let's define positive shear and negative. So first, let's imagine that we take a section right here. and this is just a differential distance dx. So I've taken a section out of the beam, and then let's draw it right here. So if I look at the left side, you can see this is the cross section, the whole height of the beam. That's 5 kips, and based on statics, the other side is resisting. This is a differential. This is dx. Now if I look over here, and I take a cut right here, this is the height of the beam that I'm showing, the cross section. This is the differential distance, dx. You can see this pushing up 5 here, and then the other side, based on statics of this, took a slice out of it, okay? It has to be down like this or 5. And that's significant because if you look at these two, they're opposite, right? If you look at the two little segments we cut. On the right side, this is going up, this is going down. On the left side, that's going down, that's going up. They look similar, but they're opposite. And then that helps explain why this is +5, this is -5 at that location. So now let's look at our definition of positive shear. So this is the height of the section. This is our definition. Shear, positive. So over here, you can see it's consistent with up on the left, down on the right. This is a differential length. And then here, you can see it's opposite to that. And then that explains why we're negative here and positive here. That's how we define positive and negative shear for any load and for any type of structure. That's shear. And then moment, I'll draw the moment diagram here. And this is in units of kip feet. That was in kips. This is in kip feet. We have A, C, and D. This is A, B, and then this is C in this location. So we've already said that if it's free to rotate, then it can't hold a moment, right? In order to, as you load, in order to develop a moment, you would have to prevent it from rotating. When the beam's free to rotate at the pin and roller, we could switch the pin and roller. That could have been a pin and roller, doesn't matter. The pin, the only reason we have a pin is to define it as not translating horizontally, right? But in terms of the moment, there's 0 bending moment at this point and at this point. It's just a roller, it's free to rotate. It can't resist hold a moment. So we know this is 0 here, and this is 0. So we have 2 points. I also know that the bending moment in the beam at any point is the force times the distance, right? So at this point, it's this force times 0 distance, that's 0 moment. If I go out a little, it's this force 5 kips times, distance. And as I go further, when I get to here, it's going to be 5 times 10, which is 50 kilo-feet. The bending moment is increasing linearly with distance. So I can just draw a straight line like that, and it's the same thing from here. 5 times 0, that's 0. 5 times 1 foot would be 5. 5 times 5 is 25. 5 times 10, and it goes over. As you go past this point, if you started from this side, it would be 5 times the distance all the way up to here, minus this 10 times that distance. You're summing all the moments. And again, each cross section is not just resisting any shear force across that section with the shear distribution equation of VQ over IB, which we'll see later, but it's also resisting, each cross section is resisting its own moment. It has this shape like this. The value is at this, so in this case, these two, we only had to calculate 1 point, is 5 times 10. Say 5 times 10 equals 50 kilo-feet. This is 50. That's it. So that's the shear diagram. This is our moment diagram for this particular structure under that load. And then let's add what's positive and negative moment. So if we take again the slice, the beam, the x, our definition of positive moment is this. On the left that way, M. On the right this way. For if you have a moment applied here, by statics, this has to be on the other side of it. If you cut out a whole segment, it has to be equal and opposite. And so you can see, looking at this, if we look at this slice, you have this force times its distance. That's clearly a moment like that, which is consistent with this. If you look at this force times this is a moment this way, which is also consistent with what's on the right there. So that's why this is all positive moment and there's no negative moment. Whereas in shear, there's positive and negative shear. And then if we look at the element including positive shear and moment, it looks like this. We got the shear and the moment. So this is our definitions of positive shear and positive moment. That instructs us how to draw our shear and moment diagrams. So these are the demands, and then you have capacities. And when it gets more complicated, and let's say you're designing a bridge structure, and I've done this before myself, you have live loads moving around. What you end up with is a shear diagram, moment diagram. Those are what we would call demands. That's what the structure has to be able to resist based on the applied loads, whatever they are. And then you have capacity. So you design your section, different size, different amount of reinforcement, steel reinforcement inside it. If it's reinforced concrete or pre-stressed concrete, if it's a steel section, you design it and then you can determine the capacity. And then of course, then you plot on top of that the capacity in moments and shears. And in all cases, of course, the capacity has to be greater than the maximum demand. Otherwise, that location where they cross over is where it's going to yield and fail. And sure enough, that's what you do. You actually plot these shear and moment diagrams for all spans of all parts of the structure, and you make sure your final validation of your design is that no points cross over, with a certain margin of a factor of safety. Otherwise, the structure is not going to be able to support the loads. And that particular location where the capacity and demand curves cross, that's the location of the future failure structure. Positive definitions of a moment shear here, and if you have opposite that, then it's going to be negative. Let's look at a distributed load on beam. Evenly distributed. This is 3 kips per foot, 50 feet long. Deformed shape like this. Greatly exaggerated, deformed shape vertically so that you can see it, but the ends, the pattern of the displaced shape is clear. The ends are free to rotate. We have reaction A and reaction B. You can solve those based on statics. So this is 75 kips. 75. Because the loading is symmetric, it's an evenly distributed load. The total of the reactions add up to be 3 times 50 is 150, divided up by 2, and that's 75. Those are our reactions. In this case, as often, there's no longitudinal reaction. The shear diagram in this case looks like this. first, this is A and B. When we first enter the beam, there's a force up when we cross over A of 75,000 pounds. That's the distributed load, but that takes time to add up, right? There's 3 kips per foot, but in the first, let's say, inch, when you just move into the structure, all it feels is that 75,000 pounds up. And then over time, it's minus 3 times any distance. But if the distance is 0, it's 75. So here is the left is 75. On the right, it's also 75 here, but it's going to be minus 75. Let me see why in a second. You can always write an equation for the shear diagram. In this case, you don't really need to, but if you want to, it's the shear. This is x is 75 minus 3 times x. So you can see at x is 0, the shear is 75 kips. And at x is 50, the shear is minus 75, right? 75 minus 3 times 50, so 75 minus 150 or minus 75. And then the shear looks like this. This is a linear equation, right? Equation of the line. It starts at 75 and it goes to minus 75. It looks like this. And it goes through 0 in the middle. And that's true for symmetry. That's our shear diagram. Notice it's positive shear to the left, negative shear to the right. So you can see at the beginning, if we take out a little segment, this 75 up, it has to be 75 down. This is clearly positive shear. That's why it starts as positive. If you look at the right side, over here, notice this is minus 75, right, at B. This is A. And if you take a slice here, and then draw it over here, you see on the right, there's a 75 kips, like this. And there's 70, it has to be 75 down. This is a differential segment. So they have to be balanced. And this is opposite to that, so this is a negative shear. And that's why this is a minus 75 there. So we could have just gone straight to here and said, oh, it's minus 75. Because it's a distributed load, the shear diagram is going to be a linear variation. And let's look at the moment diagram. It's going to look like this. Something like that's parabolic. Maximum in the middle. Moment diagram. We can write the moment expression. So here we have M. Again, this is as a function of x. So x is starting at the left and can continue all the way across. And the moment is a function of x at any location x all the way across. So this is the shear equation and the moment equation. They're both valid over the whole 50 feet. So the moment is just, I'll write it first as a reaction. R sub AX minus W x squared over 2. So this is, and I'll show why in a second. 75x minus 3x squared over 2. So that describes this. If we just draw a small portion of this, here's the 75, this is A, this is the distributed load down, and then I'm going to take a cut. I'm going to call this the moment that I'm looking for as a function of x. So this is some distance x out. This is our distributed load, which is 3. So I've cut the beam, and I'm just showing the internal moment at that location x. I'm drawing the moment this way because our definition of positive moment is this, right? So if I'm taking a cut on the right, like this, this is the internal moment, then this is positive. So this is my definition of positive moment. This is my moment in my beam. So you can see by statics, I have m. This is counterclockwise plus, let's say 3 times x. 3 times x is the total load down, right? And whatever x is. This is 3 kits per foot times x. Put a square bracket around that, and then the centroid of this loading is that it will always be at x over 2, right? No matter how far x goes. So this is the load down, and then this is x over 2. The internal moment, that's counterclockwise. The moment associated with the distributed load is counterclockwise. And that has to equal the clockwise moment, the reaction times any distance x, which is 75x. So I get m, this is the internal moment, is, as I wrote here, 75x minus, as I take this to the side now, 3x squared. Which is that. So I don't do it that way, but this explains it to you where it comes from. So I just say, oh, it's just this times this minus the moment associated with this. This is the moment in the beam here, the same as this. And I'm saying it's 75 times x, any distance x, minus the moment associated with that distributed load. You have to take the distributed load, multiply it by x to get the total load down, and then half the distance. You could use calculus also and integrate that, but you get the same result. It's not needed in this case. The only reason you need calculus for this type of a problem is if the distributed load was not a nice smooth, like either constant like this or a triangular distribution. Let's say the distributed load varied parabolically, then you'd have to integrate. And then, so we have this as a moment expression, the maximum moment. You can use this equation, or you can just determine it directly. That's it's going to be at this location here, this value. Moment max. We'll just calculate it directly. 75 times 25. So that's the moment in the middle. You can see it's the maximum in the middle. You can see this equation is parabolic. It has a second, a linear term and the square term. So that's where the parabola comes from. Comes down and gives a slope like that. And so it's the moment in the middle, 75 times 25 minus 3 times, let's say 3 times 25. That's the total load down to that point times 25. And we could have just plugged it into this equation here at x's. So it's the same thing as at x is 25 here. M max is 938 kip feet. So this is 938. That's the most important value in this moment value. Break. Okay, let's take a break. I'll be back in 10 minutes. We can say that the moment on the left, we have a moment and a shear on the left of this segment that's cut across the whole height of this cross section. And then on the right, based on statics, even though this is a small amount, we can still write m plus d. And the reason is we have m here, and then over here, differential distance over, theory, right? There's the same moment based on statics, plus there's this shear times this distance. So we have m plus dm equals m, the moment on the left of that section, plus the shear force times dx. That. We have an equal sign. There's the same moment on the left, the right of the equal sign, so that cancels. And we have dm, the differential moment, is the shear, not a differential shear force, the actual shear force, d dx. So what's interesting is we can see that v is the ratio of those two differential terms is d. dm dx. dm is just the slope, dm dx is just the slope of the moment diagonal. So let's go look at this one quite better. Or we can look at both of them. So this is saying there are two things. So we have d is dm dx, right? Differential of the moment diagram with respect to x, so it's the slope of the moment diagram. But you can also take dx to the other side, and you can say, let's say, and dm is v dx. So I'm just taking the differential dx to the left side of that equation. And therefore m, the moment expression, is just the integral of v dx. You integrate both sides of that, that becomes m, and then that's the integral. So you can, the moment is the integral of the shear expression. The shear is the slope of the moment diagram. They're interrelated, just like in differential calculus and integral calculus, where you can integrate and differentiate functions. And so here, this slope at the beginning, we have this moment expression, right? It's right there. Let's use this one's better. Okay, I'll rewrite that up here. So we have the moment expression as a function of x starting at the left is 75 times x minus 3 x squared over 2. And we can take the derivative. The derivative of the moment expression with respect to x, or calculus, is 75 minus 6x over 2. So this is 75 minus 3x. Right? And when we look at the right to shear expression, we see v is at the beginning is 75 minus, as we go out to this location, it's minus intensity 3 times any distance x. So they're one and the same, right? So that means this is 75 here. That's the slope, right? This slope is 75. Notice that that's minus 75, and sure enough, the slope is negative at the right at the moment. See this? The slope right at the end? This is minus 75. It's consistent. Look at the center right here. See this? These are at the same point. Zero slope. Therefore, zero shear. So the shear is 0 in the middle because that's the location of zero slope of the moment diagram. So we have, let's say, v equals the slope of the moment diagram. And m equals the integral, say area, of the shear diagram. So it's interesting, and they're two very different things, shear force and a moment. You know, a shear force is if you grab something, imagine a 2x4 beam, and you're trying to slide it, all the particles relative to each other. That's what shear is, across the section, okay? So it sets up a series of shear stresses across the whole cross-section. And you can look at any section, and that section, the shear stresses multiplied by their areas have to exactly add up to the applied shear force across that cross-section. At every cross-section, everything's perfectly balanced. moment is if you grab something and you bend it this way or this way. If you bend it this way, it's called positive. If you bend it this way, it's negative. And it sets up flexural stresses that change over that whole cross section. So imagine you grab something and do this. You can imagine the fibers that are getting longer on the top and shorter on the bottom. And so this is the expression there, it's MC over I. The flexural stresses, the bending stresses increase from the neutral axis up and decrease down. So if I'm bending it this way, the top fibers are all in tension, the bottom fibers are getting shorter and they're in compression like that. And yet there's this relationship between the two. They seem very different. And if you take a cross section, the bending stresses, if you integrate, sum up all those flexural stresses, these are stresses in this direction on a cross section, multiply all those little areas, those stresses by their little areas by their moment arms, that has to sum up to the applied moment at every cross section also. Everything's perfectly balanced based on statics. Let's see. So we have, we said that right here. The shear force, and this is with X starting at the left, is 75 minus 3X. We also said that the moment is equal to the integral of d dx. So this should be equal to the integral of 75 minus 3x dx, which is 75x minus 3x squared over 2. And because I didn't put limits on the integral, this has to have a constant integration. So we have the moment equation. We already wrote the moment equation before directly, okay, by summing moments, but now we're finding it by integrating the shear equation, okay, see if we get the right result. So we have 75x minus 3x squared over 2 plus c1. And we needed a constant of integration, if you remember from calculus, because when you integrate without limits, you need a constant. And the constant is solved based on the boundary conditions. And in this case, the constant is going to be 0, because we can say at x is 0, the moment is 0. So if I go all the way back to the left, we know that the moment based on the boundary conditions n is 0. So I can put that in, I put 0 here, equals 75 times 0 minus 3 over 2, 0 squared plus, so C1 is equal to 3 zeros added together, which is still 0. Right? So therefore C1 is 0. And this goes out, and then this is your moment expression, which is the same thing we wrote down based on whatever it was, directly looking at the moments at the top, 75x minus 3x squared. Now this is a structural engineer won't solve the moment expression this way, but still you understand the interaction between shear and moment. And then, of course, we can just say the shear, as I did above, is dm dx. So the shear is equal to, now I'm just going backwards again, taking the derivative of the moment expression with respect to x. You can see I get 75 minus 3x. So we get back the shear expression. So what's interesting is now you go over and look at something like this. See, now looking at this, the slope of the moment diagram is a shear. You can see this is a constant slope, right? That's why it's a constant shear. So we have here, let's say the slope at the beginning of the moment diagram. We have it's 50, and then it's divided by 10. Right? So negative, and you can see the slope on the negative side is, the drop change is minus 50 moment over 10, so that's minus 5. That's this value, it's minus 5. So positive shear, negative shear, positive slope, negative slope. In this case, it's constant slope because we have a constant shear, right? And constant negative because of that. Also, you can see this area. If you take the area of the shear diagram, we said that the moment is the integral of shear dx, which just means it's the area under the curve. This is the shear, so that means the moment. And here, there's no area. Let's go over to here. And we have 5 multiplied by 10 over 2. That's the area. Oh no, just 5 times 10. Not divided by 2 is a rectangle. So the height is 5, the length is 10. So we have 5 times 10 equals 50 cubic. And that's 50. And then it's the same if you go that way too. Okay. Let's look at some more shear multipliers.
Yeah.
Use the blue one for now. Get a black one.
Good, so good. Deflected shape. So the left, this is a cantilever, it's fixed at the left side. So there's no displacement and no rotation either. So it comes out, it's a fixed wall by definition, okay? So it's like this, something like that. We have a reaction A. There's no longitudinal reaction and a moment. So there's a moment on the wall. So imagine a moment, it's like my hand doing this, my finger pulling this way, my thumb doing that. That's the direction of the moment. That's resisting, that's the moment that's resisting 100 times 30. So of course we have summation of forces over y is 0. Reaction A. That's the vertical reaction, that's 100 kips. And then the moment A. So the shear reaction on the wall is 100,000 pounds. Same as the applied force down, it's balancing that. So everything's balanced vertically, and then for the moment on the wall, it says 100 times 30. That's a lot of moment. That's 3,000 kip feet. And a kip is 1,000 pounds. So let's draw the shear diagram. It's positive shear and it's constant over the length, it's 100. draw the moment diagram. So your maximum bending moment, where the structure would fail if you kept increasing this load, is right there. That's the moment increases. Zero here, there's a point load. So if you take, let's say, a differential distance to the left of the point load, the moment is the force times zero, right, or the dx. So the moment is increasing as you're going out, and it's linearly increasing with distance. So force times the distance, and it's the maximum. So the moment diagram is going to be triangular looking. This straight line, it's negative bending. The whole thing is negative bending. If you take a slice here, you can see that force times that, some moment that way, and on the other side it's like that. So this is negative bending at all locations. It's opposite to our positive definition of moment. And so here this is minus 3,000. This is moment and Q. So it's plotted on the negative side, and that's our moment diagram. Notice how for most of these problems, I'm just calculating like 1 point. You don't have to always write equations. I didn't write a single equation for shear or moment diagram. I just drew it. Just calculated 1 point. This is 1 point. This is my moment diagram. And you can see the slopes and the areas, they all add up, so the shear and moments are interrelated with each other. Now what's interesting is, so we can say the shear is the slope of the moment diagram, which is correct, right? We have the shear, so the slope is, now it's interesting, so we have negative moment diagram, but as we're going from left to right, the slope of the moment diagram is positive, it's going up. So it's 3,000 divided by the length of 30. So you cancel one of those with those, so you get 100. And that's the 100 here, so that's correct. And then we said that the moment, and I'm intentionally going to do this one, I won't do it on each of them, is the integral of the shear. And let's write the shear as an expression. The shear is just 100, positive 100. So this equals the integral of 100 dx. And so that's 100x plus C1. And I'm doing this to show you that that constant of integration sometimes can be important. In this case, when x is 0, there is a moment. So we have to take that into account. So we have, here we have the moment is 100 times multiplied by any distance x, this being x, plus a constant C1. And then we can say at x is 0, the moment, at x is 0, the moment is at 0, it's minus 3,000. So we have 0, no, not 0, minus 3,000 equals 100 times 0 plus C1. This goes out, so C1 is minus 3,000. And then therefore we have M is minus 3,000, which is C1, that value plus 100. So it's not just the area under the shear diagram at the moment, you have to take into account the initial moment. That's what this is telling you, okay? But the change in moment is the area. So here, if we put in x is 0, we get back minus 3,000. Imagine this is x. And then if we put in x is 30, then we get back 0, and then it's a linear variation. Of course, we could have just written the moment expression. I mean, we take a cut here, we can just write it directly. We don't have to go through all of that. It's just 100, this force times the distance x, and then you need to include the moment, which is, when I'm taking moments about an axis coming out of the page at x, 100 times this reaction A times x is a clockwise moment, that is a counterclockwise kips per foot. It's 10 feet. We have a reaction of 12 kips. That's just 0.12 times 10. And we have a moment on the wall of 6 kips. The shear diagram for this, at the very left, it starts as 12. And at the right, it's 0. There's no shear on the right. There's no sudden reaction. This is the distributed load. So it looks like this. Should we go through 0 on the right? 12 and 0. This is A and B. We have the moment diagram. Looks like this. So it's positive shear decreasing to 0 at the right. The moment diagram is going to look like this. This is minus 6.0. Moment expression, so if this is x, shear expression is 12 minus, that's 12 kips at the beginning that the cross-section feels, minus 0.12x. So if x is 10, you get back 0. If x is 0, you get back 12. You have m is 12 times this distance x, right? Minus 6 minus 0.12 x squared over 2. Now remember that the shear is the slope of the moment diagram, and the slope, the shear is 0 over a b, and so the slope of the moment diagram, that's why it's drawn like that. It goes like this, and it comes to exactly 0 slope at the right because the shear is 0. And you can take the derivative of this and see that when x is 0, when x is 10, the slope of the moment diagram is 0, which is equal to the shear. One more before we stop for the day. This one we're going to apply a moment. Simply supported beam, not a cantilever. We have a moment applied clockwise in the middle of 100 kip feet. A deformed shape like this. We have reaction A and reaction B. Solved for this before, so this is 60 feet for the length of the moment applied in the middle. This, based on statics, this comes out to be 1.67, and this is 1.67 kips. And so you can draw directly the shear diagram. interesting is we're applying a moment in the middle, but it's not a vertical force, and therefore the shear doesn't change. So we have minus 1.67 all the way across. That's the shear diagram. Moment diagram looks like this. So this is, when you have a curvature like that, that's called negative bending, and this is positive bending. The way it's gonna look is it goes down, it starts at zero, it's zero moment at both ends, internal moments of the beam. If this is a straight line, like this. And then it jumps up by 100 as it crosses there, and then it's a straight line back to zero. And you just have to calculate 1 point, well, 2 points. This point, this point. This is your moment. A, B. And this value there, if you take a cut just before the moment there, it's minus 1.67 multiplied by 30. 30 minus the differential distance. So that gives me the minus 50. That. And then the same thing, if you take a cut just to the right of that moment, you have a positive 1.67. Positive up times 30 is plus 50. And then that's this value. So this is plus 50 minus 50. Okay. Negative bending, positive bending is your moment diagram. This sudden change here, this from here to here, that's the 100 that's being applied. They have a sudden change in moment that goes from maximum negative and maximum positive. This changes. Okay, that's it. See you tomorrow.
The moment again is the top Y value 150? What is that? What is positive 50? Positive. Oh. God.